Hello everyone, I welcome you all in this presentation. In this presentation, we are going to discuss about one of the advanced manufacturing process, that is abrasive jet machining. As the name suggests, that abrasive means the abrasive particles, okay, and these abrasive particles are made up of either alumina, Al2O3, silicon carbide, or it can be a glass beads. Means generally the particles which has a very high strength, okay, and that are random in shape, okay. Next is jet means a very high velocity we are using, a very high velocity, and the machining means the removal of the material. So if the removal of the material takes place because of the abrasive particles which is moving at very high velocity, this process is called as the abrasive jet machining, okay. So in this video we'll discuss about the principle and the working of the abrasive jet machining, as well as we'll also discuss about the uh, how the removal of the material is affiliated when we are using a brittle material and when we are using the ductile material, okay. So let's start with the principle. I'm using this figure to tell you about the principle, that is this is basically the nozzle, okay. So this is the cross section at the entry point and this is at the exit point, okay. This is a workpiece at the initial level, okay. Now when from this side the abrasive particles are coming with a very high velocity, okay. Now this is basically this is a cylindrical portion, hollow cylinder inside the nozzle, okay. But generally the meaning of nozzle is decreasing the area or increasing the velocity, but here I am just using because here I am using this hollow diameter, means this hollow cylinder, means whatever the abrasive particles has the velocity at this inlet, okay, the same velocity we have at the exit point. It means that if if we have sufficient high velocity at this point, okay, at the entry point, if we do not want to increase the velocity, what the velocity of the particle over here, if we do not want, means in other words if we want the same velocity over here, then we can use this hollow portion, okay, means the same diameter or the same, yeah, same diameter or the same area, okay. But in case if we want to whatever the velocity of the abrasive particle that we are getting over here, if we again want to increase it, okay, then we can use this section as a taper section, okay. So that angle we can make over here, fine. So whatever the velocity will be here, the velocity will increases of this abrasive particle over here because the area is decreasing, okay. So that option is available. So this nozzle is basically a adjustable type nozzle, okay. So this is a nozzle, and when these abrasive particles which is exit from this area, so when they will exit from here, which is at very high velocity, they will impinge or impact over the surface of the workpiece, okay. So when they will impact over this surface, they will remove the material from the workpiece, okay. Now these abrasive particles which is coming from this exit area, that are in random in shape, that are random in shape, or generally for easy calculation of the material removal rate, MRR, we are considering in this process, we are considering that are in spherical in nature, okay, but generally they are random in nature, okay. Now the size of this abrasive particles are in the range of 10 to 50 micron, okay. So this is a very small size. So whatever the material that is removed, that is in the form of microchips, okay. The material is removed from the workpiece surface, that is in the form of microchips, okay. Next is yeah, one of the processes we call this process abrasive jet machining, is a completely a mechanical process, okay. A mechanical process means we are using here, we are using the pressure energy, okay. That pressure energy is converted into the kinetic energy, okay. So and this kinetic energy means the abrasive particles which is over here, that exit area, and when they will impinge over this surface, they have some kinetic energy, okay. So the kinetic energy, because of the kinetic energy only, the material is removed from the workpiece surface, okay. So this is completely a mechanical process in which the pressure energy is converted into the kinetic energy, okay. Next is, Yeah, abrasive particles are impinge on the workpiece surface, that I have already said. Okay, so this is very simple principle of the abrasive jet machining. For the for the easy understanding, I'm using this figure for the working of this process. So this is initially we have a air compressor. Okay, means compressor which is used to store air, that is compressed air, or it can be a CO2 gas, or it can be a nitrogen gas. Okay, so gas also we can store, uh, which is connected with a pressure gauge. So whatever the pressure is required for this compressor, okay, so that accordingly managed. After that, I forget to mention over here that there is a pressure regulating valve we are also using. So what the pressure is required, or what the velocity is required, accordingly we are maintaining this pressure regulating valve. Okay, so there is a pressure regulating valve. After that, there is a dryer. So in case of the gases, which is if liquid particles are there, then because of the dryer, uh, all the it will become dry. That liquid portion will not move forward. Okay, so that's why we are using dryer. After that also we are using the filter. So in case, like, it has become completely dry, but in case if the large molecules cannot move further, so for that also we are using a filter. Okay, when this dried air, which is very high velocity, which is move forward, and that will come first in mixer. Okay, so in this mixer there will be a mixing between the air and the abrasive particles. Okay, so this is basically a hopper we are using. Okay, this hopper, in this hopper we have to keep this abrasive particles. Okay, so when this air which is at high pressure will come in this mixer, at that time there is a wall, so we open this wall and we'll allow this abrasive particles to move inside the mixer. Okay, now there is some specific ratio is also there, that at how much pressure, means how much amount of the air with respect to this abrasive particle, so that ratio we have to maintain. And we are also using one more thing, that is electromagnetic shaker. Okay, this mixer is connected with the electromagnetic shaker. So means electromagnetic shaker we are using because when these particles, means air which is coming in this mixture, that air, we cannot decide a specific direction to this air in this mixer, that is moving randomly. Okay, that moves random direction in this mixture. Okay, so we cannot keep constant in particular direction. So when they will move random in size, there may be a chances that this abrasive particle which is coming from this side, they will gain some velocity or not. But if they will not gain the velocity, they will come below portion of this mixer. Okay, so because of that we are using the electromagnetic shaker, so that will continuously shake it, and this particle should be a complete mixture will be formed. Okay, so when this mixture is formed, this will move, which is the now it is not the air, now the abrasive particle, which is our very high velocity. Okay, so now they will enter over here, and that this phenomena what happen over here, so that we have already seen in the principal part. Okay, so there is no need to discuss over here. So this is basically a simple working of this abrasive jet machining. Okay, next is, yeah, again I'm using this figure because there is a one most important characteristic, that is this distance. We call this distance as a standoff distance. Okay, now this, the range of this standoff distance in the range of 0.50 to 5 mm. Okay, why it is important? Because we are using the abrasive particles, means how it will affect this, means what is the meaning of it again. So if if we are using this workpiece over here, and we are assuming that this standoff distance is lesser than 0.5. Okay, now it can be a 0.2 or 0.3. So whatever the abrasive particles which is coming at very high velocity, so they will impinge over the workpiece surface, and they will remove the material. Okay, because of the impingement, so they will remove the material. Now after impinging, this abrasive particle will not be the part of this workpiece, they will come out. Okay, once the material is removed, they will come out. Means what is happening, material is removed because of the collision, means because of the impact. So once the impact is completed, once the impact is done, when this abrasive particle over here which impact over this surface, it will also reflect. Okay, and this can be in any random direction. So if this distance is very small, then there may be a chance that it will stuck over here, means this abrasive particle will, which is over here, it will collide with this, um, either it will collide with whatever the particle that is coming out from this nozzle, and there may be a chance that it will impact over this nozzle portion. Okay, so the exit of this nozzle will also be wear out. Okay, the material is removed from the nozzle section as well. Okay, so we do not have to keep that, we do not have to allow that thing, so that's why we need a minimum distance, that is 0.5 mm. Okay, now one second thing is, if we are like, if this distance is greater than 5 mm. Okay, if this distance is greater than 5 mm, then what will happen that the abrasive particles which is coming from this exit, so it will not like move straight. Okay, means this is straight section that we are using, so it will not move straight, it will disperse. Okay, the cross sectional area uh, means it will be dispersed like this. Okay, so it will be dispersed like this, it means that whatever the amount, means amount of the abrasive particle which was over here, after some time it will be over here. Okay, now what happen if this is a one section and this is two section, then q means the amount total volume of the abrasive particle per unit time will be equals to a1 v1 equals to a2 v2. So this is one section, this is two section, so area is increasing, this area is increasing, it means velocity is decreasing. If the velocity is decreasing, it means that it is just like a shower. Okay, shower of the abrasive particles. So what will happen because of the shower, it will not remove the material, means this process will be means there will be no meaning of this abrasive particles, means okay, so because that will not remove the material, so we have to keep that mind, that's why we are using in the range of 0.5 to 5 mm. Okay, so that is please keep in mind, that is very very important criteria in this abrasive jet machining. Okay, uh, next is the distance between the nozzle is important criteria that we have already seen, and the abrasive particles which is in case if it is a brittle material, okay, then when it will this abrasive particle which collide which impact over here, that will remove the material. Okay, that is generally happen due to the brittle fracture, and the material which is coming out from this workpiece surface, that is in the form of microchips. Okay, now that abrasive particles that we are using, that is are very less in shape, that we have already said that 10 to 50 micron. So we also call these abrasive particle as a grits. Okay, so please keep in mind this thing. Next is process parameters. When the abrasive particles that we have already seen that this is alumina or silicon carbide, or it can be a glass beads. The shape of this abrasive particles is random, that is spherical or irregular. Okay, that is in the range of 10 to 15 micron. Okay, the gas carrier gases, either it can be air, carbon dioxide or nitrogen, and the pressure in the range of 2 to 10 bar. Okay, another few more parameters are there. So abrasive jet, the jet that we are using, the velocity of that jet, that is in the range of 150 to 300 meter per second. The standoff distance that we have to maintain it in this range, and the impingement angle is 60 to 90 degree. Okay, next is the nozzle material, because inside the nozzle uh, the abrasive particles are moving, so these abrasive particles which is at very high velocity, that will collide inside the nozzle as well. So we have to maintain this nozzle with a very good strengthening material. Okay, so that is we are using the tungsten carbide or the sapphire. Okay, the diameter of that nozzle is in 0.2 to 0.8 mm. Okay, please keep in mind. Next is modeling of MRR. Okay, now to consider to calculate the MRR, material removal rate, we have to need some assumptions, and after this assumption I will tell you that how we have to maintain this MRR for the brittle and the ductile material. Okay, so assumptions are, first is we have to consider this size of this grit that we are using, or the abrasive particle that we are using, that is in spherical in nature. Okay. Second is the kinetic energy, the abrasive particles which is moving at very high velocity, that has some kinetic energy. So when this kinetic energy will collide with the means impinge with this particles will impinge over the workpiece surface, the complete kinetic energy is transferred to remove the material. Okay. Next is the brittle material are considered to be fail due to the brittle fracture, and the volume is considered, maximum volume is considered as a semi-spherical. Okay, that will I will tell you. Now ductile material. Okay, so this I will inform that this I will tell you. Okay, so like this is the two figure that I'm using. So this is the workpiece that is of the brittle material, and in this case this material is of ductile. Okay, now this is the average size of this means spherical size we are considering of this abrasive particles. Okay, and these are the grids or a random shape over this particle. Okay, now when I'm just first talking about this brittle material, when this abrasive particle which come in contact with this surface, okay, that will remove the material from this surface. So this material is removed. So when you will look it from the top view, it will look like a circle. Okay, over here, okay, sorry, over here it will look like a circle, and from this perpendicular to plane, if you will look it, then there is some specific depth. Okay, now when you are taking this is a center, then it has some radius over here, this r, and this radius is constant through this depth. Okay, so this is it. If you look it in a 3D, it will be like a spherical, means semi-spherical or hemisphere, whatever it is, but a volume that is removed, it will be looks like a sphere, a part of a sphere. Okay, now the maximum thing is can be possible that if this is the diameter of this grid, that is dg. Okay, now there is a possibility that when it will collide over here, this is the maximum diameter that can be covered uh, while removing the material. Okay, so if this is the maximum diameter, then this material which is removed from this surface, it will be like a semi-sphere. Okay, because this half portion of this abrasive particle is inside the workpiece surface. Okay, half portion, complete half portion. So it will be like a semi-sphere. Okay, so that's why I have mentioned over here that the fracture volume is considered to be semi-sphere. Okay. Okay. Okay, so next is for the ductile material. Now in case of the ductile material, when this because ductile material has some ductility or the plasticity, so when this abrasive particle, which when it will collide, sorry, when will they will impinge on the workpiece surface, there may be a chance that when it will impact, there is just a impression, they just leave an impression on this workpiece surface, and they will reflect it. Okay, there is a possibility. Another is they just whatever the shape of this points over here, they will just indent inside this ductile material, and they will reflect. Okay, the moves out. So means they are just leaving a specific indentation over here. Okay, so this indentation, and this indentation is same in this brittle material as well. Now but the in case of the material not same, but in the brittle material, whatever the depth that is inserted inside this workpiece of this abrasive particle, we call this depth as an indentation. So uh, they just leave a specific impression over here, so that in ductile material we are calling that impression as a indentation, and over here in this brittle material, whatever the amount of the material that is removed inside the workpiece material, we calling that as a indentation. Okay, so this is the phenomena or the mechanism that in case of the brittle material and the ductile material. So now if we have to remove the same amount of if we have a same size of the workpiece, okay, and we have to remove the material from the ductile as well as the brittle material, sorry, ductile and the brittle material, then we have to impinge more abrasive particles on the ductile material. Okay, because they are just leaving an impression and they are just coming out. Okay, so if we have to remove the same amount of the material in case of the ductile material, then we have to apply abrasive jet machining more time in comparison with the brittle material. Okay. Next is we are considering this volume. So this volume which is, yeah, in case this is the center I am considering, and this is radius r, small r I am considering for this region. Okay. Because this is also a sphere kind, this is a part of a sphere, and if you will make, then this will be another sphere. Okay. But this diameter of this sphere is lesser than this diameter. Okay. So that's why I am using I'm considering that this diameter of this grid is dg. Okay. So in case of if I have to write the radius, then it will be rg, but I am not using rg, I am using dg by 2. Okay. Now this is the maximum radius or the maximum diameter, and I'm using over here, that is radius is r. Okay. That is a small r, and maximum can be possible, that is rg. Okay. Or dg by 2. Now when I'm using this r, it means that the volume that is removed from the workpiece surface will be semi-sphere. Okay. Because this is a complete sphere, so it will be a semi-sphere. It means that the volume will be 2 pi r cube. Okay. So this is in case of the brittle material. Now in case of the ductile material, the same we have to consider, this is the radius of r, but we are not sure because different professors or different researchers has given the different formulas. In case of ductile material, the volume removed is equals to, if this is the indentation, this is delta, so the volume will be given as pi delta square into dg by 2 minus delta by 3. Okay. So this is the formula that has been given by the researchers for the case of ductile material. Okay. So the volume for this brittle material, in case of the brittle, that is 2 pi 3 pi r cube, and for this ductile, that is pi delta square into dg by 2 minus delta by 3. Okay. Now one important calculation is we are assuming that this when in case of the brittle material, that this is a center of this grid, and this is radius r. Okay. This AB is radius r, and this is the indentation. Okay. Now this delta, this is the radius rg, or we can say that is dg by 2. Okay. And now in case of the triangle OBA or OAB, now if you look this OA square, that is hypotenuse square, will be equals to OB square plus AB square, means OB square plus AB square. Okay. Now this OB is equals to, this is equals to RG or DG by 2, and but this is delta, so this will be like DG by 2 minus delta. Okay. And plus AB square, so AB is equals to R. Okay. And OA is equals to DG by 2 square. Okay. So the next is DG by 2 whole square equals to DG by 2 minus delta whole square plus R square. Okay. I'm just taking this this quantity in this side, so this R square will be equals to DG square by 2 minus, I'm just opening this A minus B square in the form of that, so that's DG by 2 whole square minus delta square, so minus minus will be plus 2 AB. Okay. So this will be like DG, this will be term will be cancel out. Now delta is very small, so I'm just considering this as a 0. This 2 will be cancel out, so the R will be equals to root DG into delta. Okay. So this is R equals to root DG by DG into delta. Now I'm just putting this value of R in this, that is that will give me the 2 by 3, that is DG by DG into delta in raised to cube, and this is 1 by 2, so this will be 3 by 2. Okay. Now by the way, this R value is not over here, but is this DG by 2 that is greater than, very greater than delta by 3, so just we are considering that this delta by 3 is 0. Okay. Over here, so this VD is equals to pi into delta square into DG by 2. So this is the volume that we are considering for the ductile material. Okay. In case of delta, and this is for the case of brittle material. Okay. Okay, so in this video we are stopping up to here. In next video we'll discuss about the kinetic energy and the work done, and the material removal rate in case of brittle and the ductile. Thank you so much.